Welcome to Extended Reality, or XR, with ArcGIS. My name is Rex Hansen. I'm a product manager for ArcGIS Runtime and the new game engine products. I'm usually joined by Stefan, Pascal, and Adrian, but they're unavailable for this session, so I'll be walking you through ArcGIS and using extended reality or building extended reality experiences with ArcGIS for the next hour. First, I'd like to start with an overview of a couple terms that we'll use through the session, just so that we can be on the same page with respect to their context. The first one is VR, or virtual reality, which is really all about being there. It's really teleporting to another location that is similar or different than the real world. In general, you can view, move, and interact with the virtual world, often depending upon the device inputs that are provided. Here's an example of a VR experience that provides different urban plans within a city. In this case, we have a VR device on a mobile device with a set of different inputs that allow for selecting different viewpoints or different experiences here. In this case, both with and without a structure. You can see how it might affect shadowing, different development options, and of course, rejoining reality. That's a good thing. Great. So the next topic is AR, or augmented reality, which is really all about interacting with the real world by overlaying virtual content, which often has meaning in the real world. This video shows route guidance to an office. The user's geographic position in the real world is the start point. The office of interest is the destination. As he enters the office that is the destination, he'll get a route, a heads-up route, really virtual content that's overlaid on the real world through the device camera, and then provided and enabled for them to be able to follow through in the physical world and use that virtual content to guide them to the next location. Now in this case we're working with world scale, and so we have a network data set for this building. This is a building on Esri's Redlands campus. Being able to traverse between two different floors and follow the path or the route that was calculated through a network data set. From the start point to the destination, we get a nice view here of a couple of the developers who are building this experience. And we can see the virtual content guides us through a set of arrows to the destination. A little assistance to get through some physical obstacles here. And then over a couple of objects. And finally to a destination. There we go, to Sud Menon's office. Fantastic. So a great example here of being able to work with augmented reality experiences on a mobile device, like a smartphone. The next term here is mixed reality. And really mixed reality is all about immersing virtual content into the real world. Really kind of the next step of augmented reality. Here's an example of virtual content with some holographic and some traditional geometries represented at full or world scale to view plans and structures in the field. And so you can see at full scale, different buildings may be present on this street, and being able to visualize them while on site in a real world geographic location. In this case, working with displaying that holographic content with a binocular view. In this case, you're using a Hololens device, but also being able to use hand gestures to be able to interact with different experiences here. Of course, the toolbar itself is virtual content presented in relative space near the device. So this is showing traditional geometries or features on a surface. Being able to traverse the physical world here. Able to see how those features interact with or intersect with the physical world. These are actually not seen. This is a water system below ground. So being able to see where that water system is located, but then also overlay it with additional content. And these other electrical systems that show how the systems themselves are present beneath ground and how they're related. And then also simulate real world objects such as a train in this space. course, a little bit of the work that's going on behind the scenes here in building out a structure or a prospective structure and being able to visualize that structure using a HoloLens device. Now, this is a tabletop experience. We'll talk about that in a little bit. Being able to view a model at a small scale and interact with it very naturally, but then also take that same experience and use it in the real world and iterate through different options or different views of that same structure. Again, hand gestures to be able to manipulate or change and scope the different viewpoints. So an additional structure on a street here, converting a parking lot to a usable building or space. Great, so something that we see often with HoloLens and Magic Leap, all of these kind of come together in something called extended reality, which is a term used to describe the full spectrum of AR, MR, and VR. Now, when transitioning from the physical world to extended reality experience, you can choose to supplement the real world with virtual content, whether overlaid or merged, small or full scale, or choose to completely immerse into a virtual experience. So these are the terms and concepts that we'll continue to reference in this session going forward. Next, we'll talk about the positional tracking for extended reality experiences. Now, primarily for VR devices, but can also apply to AR, MR. Different techniques for tracking hardware movement, like headsets, is necessary to provide a natural or reflective response to physical movements. Inside-out tracking uses cameras or sensors on the device being tracked, and outside-in uses sensors placed in stationary locations around the device or around the camera. Outside in can be a bit more difficult to maintain, actually restrictive and sometimes more expensive. Inside out is usually the preferred method as it relies on sensors in the device being tracked. Markerless as a VR experience doesn't require a specific physical object, just really relative surfaces determine the position, the orientation to respond to head and device movement, so it feels natural. That said, AR or MR devices can also leverage this technique to determine orientation, but marker-based tracking can provide initial positions in the real world important for AR, MR experiences. Markers can include things like QR codes, IR markers, natural features or objects that are recognizable and stationary with a well-known, predetermined geographic location. Movements of the AR, MR device can use these controls or spatial anchors to provide a more accurate location. Of course, in the AR/MR space, positional accuracy is critical to overlay or merge virtual content in the correct location. So other sensors and techniques can be used to provide varying levels of accuracy, from GNSS to Wi-Fi to 5G to beacons, RTK positioning, all provide varying levels of accuracy and cost. The goal here is to use the appropriate level of accuracy to deliver a usable AR/MR experience at an affordable cost. Next, let's take a brief look at XR devices that exist in the marketplace today. So a significant number of XR devices exist today at varying costs with different benefits and drawbacks. However, the market is still somewhat dynamic. For example, a number of startups in the AR headset or mixed reality space have gone out of business as stronger, more well-financed integrated systems have succeeded. On the VR side, premium and mobile systems have started to converge. Both promote 6 degrees of freedom and inside-out markerless positioning. Mobile hardware is getting better, though, with dedicated chipsets to deliver better VR experiences. It's still difficult to match the graphics capability and the computing power of VR systems tethered to a PC, though. One special mention or exception here, and an example of this convergence is Oculus Quest. It can function as a mobile device, but also connect to and leverage a PC for a premium experience. To minimize hardware and mobility, hand tracking is supported, but more discrete control over movements is available with optional controllers. With respect to mixed reality, HoloLens 2 has made some impressive improvements to their popular platform. It has a much better field of view, integration with spatial anchors, you can offload graphic rendering, and support for Unreal Engine, in addition to Unity, really open up more opportunities in this space. Next, let's take a look at XR user interface concepts and get a better handle on some of those concepts. One is a table scale, which is a common pattern within the XR space. In general, tabletop or table scale represents a virtual small-scale representation of a model or a real-world object, a landscape or features, really just a scene. This virtual representation can fit on a tabletop, thus table scale, but that's just incidental. It could be represented on a floor or any other surface. These sandboxed experiences are generally used for design and collaboration experiences. It's intuitive as it represents a small-scale model, which in the past may have been constructed out of a physical material. As it's intuitive and grounded in the physical world, motion sickness usually isn't a problem. Teleporting is a technique for moving between locations in a VR experience quickly. Sometimes these positions are predetermined if the VR experience author defined a limited set of perspectives. Sometimes they're less restrictive and enable dynamic discovery. It really depends on the scenario. As motion sickness can be an issue with VR, teleporting is usually an ideal way to get around without adverse experience. Unfortunately, it can cause a loss of positional perspective, orientation, so something to consider if important for a VR user. Now, interacting with the virtual environment presents a number of challenges. How to provide the appropriate level of control without requiring more hardware is critical. So think about using a mobile device with your stylus versus your finger. Often this depends on how much precision is necessary. Controllers can provide fast and consistent interactive experiences, but they can be complicated. On the other hand, pun intended, hand tracking doesn't require additional peripheral hardware. It may be intuitive, but more coarse-grained and unfamiliar. But this area is improving. Here's a video of some of the work done by Microsoft for the HoloLens device in this area.
Fully articulated hand tracking. And as I move my hands around, the HoloLens 2 is actually calibrating to my unique hand size. Look at the way that the hologram is responding to my hand, almost inviting me to touch it. And in fact, I can just grab this corner to resize it. Or I can rotate it. Or move it. That's right. We are touching holograms. Now, it's a little big, so let me just use two hands here to make it smaller, and then rotate it so you can see. There we go. And then let me put it down here near spatial, maybe make it a bit smaller. Yeah, that's nice. Let me just call it over with my voice. Follow me. So let me just open up that start menu here, and then place the app, and then launch it. So now we're actually exiting my mixed reality home and going into an immersive experience. But notice that that browser that I had actually followed me in. We spent years exploring and refining interactions for HoloLens 2. And the playground is just a tiny sampling of the many prototypes that we built, tested, and learned from. The interaction that really took home the cake, though, was the pinch slider. The way that works is you just pinch it and move it wherever you want. And what we found was that people really like that tactile sensation of their fingers touching as they grabbed and then released. And across the board, for all interactions, the audio and visual feedback as you grab, move, and then release were all really critical for making this experience feel connected. I just love the way these move and the sounds they play when I press them.
Great, so a good example of some common tasks or experiences here, really a user experience for a heads-up holographic mixed reality experience. So some great work there, and a lot of that will start to sort of filter out or at least become more familiar as mixed reality experiences start to transcend into other industries. Next, I'd like to talk a bit about how XR impacts or how it works with or what opportunities we have within ArcGIS in that space. So next, let's talk about extended reality and how it impacts ArcGIS or how it works with different ArcGIS technologies and solutions. This chart shows different products and different solutions that can be built and delivered with ArcGIS technology, mainly to access and use GIS data. This includes things like CityEngine for creation of data and curation, export, apps that allow for you to view and visualize experiences here in the extended reality spectrum, and then different developer technologies that allow you to build extended reality experiences. So let's start walking through this. The first option here is ArcGIS 360 VR, which provides a mobile VR app for CityEngine users, mainly in the urban planning space, with an easy way to deliver urban landscapes and perspectives with predefined viewpoints. Now in this video, you'll see a set of VR projects cooked in CityEngine and shared in ArcGIS Online as portal items. The user of the app can access and load these projects to view different plans for urban landscapes and structures from a set of positions or bookmarks. This is a viable option for delivering simple, easy-to-use VR experiences to stakeholders and decision makers who have mobile devices. Thus far, it's remained in beta and available for use with Samsung Gear VR and Oculus systems. But a more viable option in the future may be to use WebVR or WebXR to reach a broader audience and avoid different store delivery issues. So this is really work in progress today. The next option here is CityEngine VR Experience, which provides an Unreal Engine project template that delivers a premium VR experience for architecture and urban planning scenarios. It includes a virtual office and a table to place and interact with models exported from CityEngine. We just released 2019.1.1, available on GeoNet, with an update for Unreal Engine 4.24 that has a better UX, UI, and a new Unreal Engine sky atmosphere model. So in this video, you'll see the VR tabletop in this virtual office. And a set of interactive controls allow you to change properties on the fly. You can use the controllers in this case to be able to zoom or manipulate some of the content. You can change different scenarios and view different content that's been created and curated within CityEngine. You can also change other properties here, which really leverages some of the capabilities of Unreal Engine as a game engine to work with real-world objects or data. Traditional navigation experiences here too. You can also use the handheld controllers as well. In addition, collaboration with another participant is an option, so you can see another participant within your virtual space here. You can see what they're looking at, where they're holding their controller. And then also you can immerse yourselves within the model itself and get a true VR experience and a different perspective of some of those capabilities or properties that you can change. In this case, you can teleport to different locations, so you don't have to manually move around, and you can zoom back out and see the full area of interest in this space. Great. Now the next option that involves CityEngine is being able to export GIS data into a static format, which can be accessed directly in a game engine. More specifically, the major players in the game engine space, Unity and Unreal Engine. Export options within CityEngine convert 3D content into FBX for use in Unity, or Datasmith for use in Unreal Engine. Datasmith is content designed for direct consumption within Unreal Engine. The key here is using as lossless a format as possible to retain the fidelity of the GIS data when used in a game engine. In general, this solution actually provides a relatively quick way to get GIS data into a game engine. Then as a game engine developer, build out great experiences using game engine technology. So our current work in this area is targeting support for FBX 2019.5 and Datasmith 4.24, 4.25, along with CityEngine 2020, 0 and 1. So there's some work going on there. I'd like to show a couple examples of how that work has come together. So these are a set of urban models, 3D models that have been exported from CityEngine, and this is using Unreal Engine. So we're working with Datasmith-based data here in a variety of different models to represent vegetation. You can see as we transition from day to night, we get a realistic experience here with lights coming on in the different buildings and getting a good perspective here of what that might look like as we transition from day to night on this perspective city street. Here's another example here of individuals walking or interacting with the environment from a street corner. You can really admire the fidelity and the smoothness of the data, the experience, and the sort of the realism that can be provided through this game engine rendering technology and being able to bring your real-world GIS data, in this case urban landscapes, into them. Now, the next option for working with GIS data is using ArcGIS Runtime, a developer technology for building or developing AR applications. Now, augmented reality with ArcGIS Runtime is now available for production use. We've delivered this last year and we continue to enhance it going forward. These are AR capabilities introduced for mobile platforms, for iOS and Android devices. These capabilities are not exposed or not available for VR or mixed reality solutions. These AR capabilities are delivered with runtime SDKs that support iOS and Android, in this case, the Android, iOS, Qt, and .NET SDKs. They're delivered as open source toolkits so that we can work dynamically with different hardware capabilities and the ARKit or AR Core capabilities that are built into iOS and Android. Now, AR capabilities in ArcGIS Runtime provide a set of support experiences and use cases. The first one is a flyover experience, which was really designed for education scenarios. This intuitive navigation of a scene with the device changes the camera's perspective based upon the orientation of the device. Tabletop, great for design scenarios where we want to be able to take a virtual small-scale model and put it in a tabletop experience, and so you can still see the camera provides a representation of the physical world, and being able to overlay or at least lock content of a scene to a physical surface, and be able to interact with that small-scale model and maybe collaborate around the design of 3D content. The last one is world scale. This is really designed for inspection scenarios, whether you're working with enhancing or non-visible objects within the real world. This is a one-to-one relationship, real world scale, where you're working with virtual content overlaid on top of a scene that represents the real world. So the camera feed represents the real world, and the scene content represents the virtual world. Being able to overlay those at a one-to-one scale and be able to interact with content effectively. Now, a good example of this in ArcGIS Runtime, this world-scale augmented reality, is an example that was built during a hackathon here by a set of runtime developers earlier this year. And a video was recorded by Nick Furness, another product manager for ArcGIS Runtime. I want to play that video so you can see some of the great work that they've done.
At 100.6, we added AR capabilities to the runtime. We expanded upon them very slightly at 100.7. In this case, we're looking at real-world GIS AR experience. The real-time locations of aircraft are being pulled from an FAA feed and updated in a scene. And all we're doing is manipulating components in a scene, and runtime knows where the phone is in the real world, and as we move the camera around, it updates the display to show that real-time GIS information overlaid on top of the camera feed. This makes it very simple to build AR applications, and in fact this was built in an afternoon during a recent internal hackathon. And this pattern makes it very easy to build other kinds of AR experiences. Runtime supports a couple of others. In this case, we look at flyover mode. We select a plane, and now the camera is locked to that plane's location as it moves through the scene. We move the phone around, we change the direction the camera is looking. Here we're looking at Big Bear. As we pan up, we can see Redlands. And if we freeze the frame for a second, what we see are the contents of the scene, in this case the user's location in Redlands, some airport, and if we look very closely, a couple of other aircraft. And again, all we're doing is manipulating items in the scene based off real-time FAA location information.
Great, so when working with world-scale AR experiences, not just with runtime, but in general, there's a number of challenges and considerations to consider. One challenge is the ability for the employer or contractor or staff member, maybe a member of the general public, to understand and use AR effectively. So often best to use the crawl, walk, and run approach when introducing AR capabilities into an existing workflow, where it's done incrementally and intuitively, and the pace really depends upon the audience receptiveness or perceived value and the complexity. The take-home is pace yourself, pace your project to achieve a notable ROI and move on from there. Another significant challenge to building and delivering a world-scale AR experience is maintaining an appropriate level of accuracy for the position and the orientation of a device. Ideally, the overlay of virtual content from a scene camera and the physical content from a device camera content matches perfectly. As the device moves in the real world, the position and the orientation of both cameras should remain in sync. In reality, limitations of devices and AR frameworks and differences in the precision and the availability of positioning systems will usually require your AR workflows to include an initial calibration effort to improve overlay accuracy. Fortunately, the runtime toolkits are open source, and so you as the developer can enhance the AR view, the AR scene view component, to use one or a combination of techniques to drive the calibration experience and maintain position and orientation. For example, you can use the device's built-in GNSS, GPS, to get an initial position, provide a UI to adjust the position of the virtual surface and the features to overlay those in the real world, and then use an AR framework, like AR Core, AR Kit, to handle changes in relative position. AR samples are included with the ArcGIS Runtime SDKs, provide initial examples for calibration experiences to help you get started. It's also important to consider the readiness of your geographic data for a world-scale AR experience. Since your geographic data needs to overlay the physical 3D world, its accuracy in the horizontal, latitude and longitude, and the vertical or elevation space is important. In some cases, the location of features may have been established using core-screened workflows and or elevation information that was not included or was not derived from a low resolution elevation surface. The accuracy required in your geographic data may differ depending on how it will be used. For example, to find the general location of a gas meter on a fairly large part of property might only require 10-meter accuracy, whereas a solution to determine where it's safe to dig to avoid a subsurface gas pipeline might require centimeter level accuracy. So it really depends. So in short, consider what is needed to achieve the appropriate level of positional accuracy for a device and your geographic area in any world scale AR experience. The next and final option is a new set of products that we plan to deliver for developers that enables access to ArcGIS data and operations within game engines, Unity and Unreal Engine. In this case, for developing a full spectrum of extended reality applications. Now, developing with game engines offers a number of benefits, such as a premium high-fidelity rendering experience, built-in options for targeting multiple platforms and devices, in many cases a significant, motivated, and passionate developer community, and rich rendering and animation options that take advantage of built-in physics and effects. Now, integration with ArcGIS, or integrating ArcGIS with the two most popular game engines at this time, Unity and Unreal Engine, really demands developer options that target gamified experiences for both extended reality solutions and just about any 3D app that needs GIS. So these Unity and Unreal Engine plugins will provide APIs to access ArcGIS data and operations, both live and local, retain real-world coordinate space, and support both local, flat Earth, and global round Earth experiences. Of course, they will integrate with familiar game engine developer experiences and include the appropriate developer documentation. ArcGIS capabilities in game engines initially target a variety of different data sources, and this includes raster tile layers that support display, such as base maps and elevation, scene layers that include 3D objects such as textured buildings, integrated mesh like a continuous surface, and point clouds that might be derived from LiDAR. It also includes support for access to feature layers, traditionally point signs and polygons, that would be features meaning geometry and attributes, as well as operations like geocoding and routing. So here's a video from the Dev Summit 2020 plenary, live streamed in March of this year. It shows Adrian Mario, our lead developer for game engines, using Unity to build a GIS app and deploy to a VR device. This shows how we'll integrate with the game engine developer user experience. It includes objects used to render a scene, project objects, and the inspector to set and modify properties of objects, and of course the viewport. Now, of course, we could build an experience with scripts, code, and such, but in this case, we'll deliver also a prefab to configure scene content without writing any code. First, we need to set the global coordinate system and set a camera position. So we'll define geocoding here near the Grand Canyon. We'll set a base map to provide imagery for context. We'll actually pull in another raster tile, a set of raster tiles here for display to overlay on top of our base map to provide better context. In this case, a nice USGS geology map coming from the Living Atlas. And we'll give it a name, add it to our layers list. And that's coming from a service. We can also work with a file, a local file, in this case a raster tile package. This includes a set of contours, in this case for the Grand Canyon area. We'll go ahead and add that layer. Now, so that all these worked well together, we'll change the opacity here so that we can see them all interact together and provide a nice enhanced visual experience. one of the benefits of using the game engine is the prevalence of high-fidelity effects to enhance the visual experience. This includes adding sky and fog for a realistic experience. We can press the run button to execute and run the app at full screen so you can really see the high-quality realistic experience. But that's not all. As we'll see here, Adrian, as a developer, and as the game engine can enable easy access to VR experiences, he'll target a VR headset, and we'll see Adrian deploy this to an Oculus Rift S that he has and fully immerse himself in a virtual experience. Great. So now he'll look around, admire the landscape, admire the realism that's built into this GIS application. There we go. Really impressive, working with a set of dynamic resources, enjoying the sky, the ground, a great perspective, and just a high-fidelity experience with a variety of different GIS data sets, all coming together with a nice realistic experience. Great, so the next question might be, well, how do I get access to this? So there's an ArcGIS for Game Engines beta program that's open today. You can join this using the URL provided here. At this stage, the first beta will be delivered in Q3, probably early Q3 of 2020, and our first production release is scheduled for early 2021. So feel free to join and start participating with our game engine offerings, our integration work with Unity and Unreal Engine soon. Great. I want to thank you for joining me today. Hopefully this was helpful. Stay healthy.